to this kind of alternative oblivion in action, it might be prolonged to 1,000 years, and by getting himself thawed every 100 years, he might learn what had happened during his frozen condition. So he didn't really think about aging being cured, but he had this idea that it could work. And in 1766, he actually experimented on this. So he placed 2 of these carp, which is a type of fish, in a glass vessel with water, and then he kept adding snow around it. And then the water froze, and then he thawed the fish, but he found that they did not recover action, so that they were really dead. So he thought this was going to make him rich, but he tried this experiment, didn't work, so he gave up on it. The next person, a little bit more famous in this area, is Benjamin Franklin. He has a letter to his friend in 1773. So he replicated a finding that if you have flies and they drown in any kind of liquid, in his case it was Madeira wine, and then they're exposed to sunlight for a few hours, they can recover. And so they clean themselves and they flew away. So he has a great quote. He says, "I wish it were possible to invent a method of embalming drowned persons in such a manner that they might be recalled to life at any period, however distant, for having an ardent desire to see and observe the state of America 100 years hence, I should prefer to an ordinary death the being immersed with a few friends in a cask of Madeira, until that time to be recalled to life by the solar warmth of my dear country." He didn't pursue it. He noted, in all probability, we live in a century too little advanced and too near the infancy of science to see such an art brought in our time to its perfection. So I think that was interesting because, first of all, he's using fluid preservation. That's what he's proposing. And also, he's kind of has this idea of, he probably was right, he probably couldn't have done it then, but also maybe he doesn't have to be perfect. Maybe preservation doesn't have to be perfect, it can still work even before it's brought to its perfection.
But Madeira is not good enough.
What?
But Madeira is not good enough.
If he had seriously applied himself to this notion, I think he might have actually been able to figure it out. The problem is, in my opinion, they didn't have the notion of information theory. They didn't understand information theory yet. That didn't come really until the 1950s when computers started being big and cybernetics came about. I think that's why Evan Cooper and Robert Ettinger were both very influenced by cybernetics and information theory.
Given what he had available in the late 1700s, how do you think he could have materially achieved?
The same methods that John Hunter and the other anatomists were using for preservation of brains. If they had the thought of, the information might still be present, it was an interesting historical question of whether they could have preserved it.
Wow, so we potentially could have had people from the 1700s.
Yeah, it's possible. Okay, Evan Cooper. So he is really one of the main first cryonicist. He wrote a book about it in 1962. He ran the first conference. He started an organization. Then he became frustrated with the lack of help and progress. He quit the field around 1970. He took up sailing and he was lost at sea. It's actually not his first name. His first name was some other thing, and then he abandoned his wife and moved to Maryland. So he's not a great guy. So he proposed 2 different pathways to revival. The first pathway was in his book. It was future medicine simply curing whatever problem killed a person and then warming and reviving the body. So he discussed the animal research on rats and hamsters that were being cooled to near freezing and revived, and he extrapolated that scientists would eventually scale this up to humans frozen for indefinite periods. So this was influential on him. He did think this would happen soon enough, suspended animation. He thought that this were not possible to develop. He drew on cybernetics to propose that a person's pattern could be scanned from the preserved body and reconstructed in a new biological tissue or transferred to a machine substrate. He actually thought most people would prefer the machine substrate reconstruction option, and today that seems to be clearly incorrect. So you kind of have these 2 things, right? Suspended animation and information preservation. Robert Ettinger, obviously immensely influential on the field. He wrote the first published book. So in his book, he explicitly distinguished body preservation from suspended animation. He said, we cannot do suspended animation, but body preservation still makes sense. But he did think that suspended animation would eventually happen. He didn't say exactly when, but in the book it seems somewhat optimistic it would happen within a few decades. And this was part of the reason why he thought that we needed this, as he called, freezer program, because eventually we're going to get suspended animation and we need the infrastructure to be able to store the bodies once they are frozen. However, although he was interested in suspended animation, he also said it makes sense to do it now before we have that available. And so he argued that as long as a person's brain microstructure is intact, even damaged, they are potentially recoverable. His proposed revival method was what I would call proto-nanotechnological. So he said, here's this quote, "Thus, if brute force methods are necessary, it is not inconceivable that huge surgeon machines, working 24 hours a day for decades or even centuries, will tenderly restore the frozen brains, cell by cell or even molecule by molecule in critical areas. We hasten to add that in all likelihood the methods used will be much more elegant and yet unforeseen." Robert Prehoda, I think, is another important figure historically. He was an early critic of cryonics and of Ettinger, although he did participate in some of the early cryopreservations. He argued that to freeze the dying or dead at the present time is totally unfeasible. When an organ as large as a human brain is perfused with DMSO and frozen to cryogenic temperatures, most of the cells are damaged beyond any conceptual means of future repair and restoration to original function. He argued that cryonics was a pseudoscientific cult, which is presenting a completely distorted picture of the prospects for suspended animation to the general public. And he was concerned that the freeze now movement would mislead the public and delay research in suspended animation. And he wanted that people to fund that research because he expected it could lead to a revolutionary impact in a few years if it was funded. So he has this book, Suspended Animation, published in 1969. Another important figure, I think, is Eric Drexler. He was, and I believe you said that this is when you signed up or first became interested. He was an early proponent of molecular nanotechnology. He was the author of a book, Engines of Creation, published in 1986. And it was actually the first time I became interested in cryonics was when I read this in college. And I won it because I was commented on his blog, and I randomly won this book because I don't know why, and I read it and I was very interested. And he proposed atomically precise repair as a future engineering discipline. And so he has this quote, I think this was from an interview. He said, "I found out that these crazy cryonics people not only were right, but they even knew why they were right, that in the future we're going to have molecular repair technology. Ettinger wrote of repairing cells molecule by molecule if need be. He had the basic physical perception that we develop molecular level repair machines and that doing this doesn't conflict with any physical law. Today, Drexlerian nanotechnology is likely the most studied conceptual route to revival of preserved people. And Engines of Creation includes a chapter describing how revival could work following biostasis. And his biostasis proposed strategy was to use glutaraldehyde fixation followed by cryopreservation. So from the beginning, he was already kind of thinking that aldehyde fixation would be compatible with this. Ralph Merkle wrote a lot about revival after preservation, including an influential 1989 article, Molecular Repair of the Brain, describing how nanotechnology could repair damage at the molecular level. He defined the concept of information theoretic depth, which stipulates that a person is only truly dead when the structures encoding memory and personality are destroyed beyond any possible recovery. And in this revision of his Molecular Repair of the Brain article from 1994, he had this note. He said, as an aside, the vascular perfusion of chemical fixatives to improve stability of tissue structures prior to perfusion with cryoprotect and subsequent storage in liquid nitrogen would seem to offer significant advantages. The main issue that would require resolution prior to such use is the risk that fixation might obstruct circulation, thus impeding subsequent perfusion with cryoprotectants. Other than this risk, the use of chemical fixatives, such as aldehydes and in particular glutaraldehyde, would reliably improve structural preservation and would be effective at halting almost all deterioration within minutes of perfusion. So I think it's clear that also Ralph Merkel's nanotechnology would be compatible with fixation. Another person I think is pretty actually important recently has been Laura Deming. So she has this company now called Until Labs. And they're trying to build reversible cryopreservation technologies. And she has this tweet from last year. She said, think the hibernation pods you see in space movies for long-term travel. We want to build that. And you can see I have a picture of such hibernation pods from 2001: A Space Odyssey from 1968. Okay, so I think that's a few examples. Of course, we can go through a lot more examples, but I want to try to draw a general principle. I think that you can kind of try to classify or think about different revival strategies based on maybe a spectrum of how much people think about whether we should be preserving information or whether we should be going for suspended animation or bust. Like either we wait for suspended animation or we do nothing in the meantime. So that would be Robert Prehoda on the far right is a classic example. So, and you talk to people like this all the time, right? They say, it doesn't work, talk to me when it works. And it's like, basically, what they're saying is, we need to get suspended animation, right? And however, that's a very difficult problem. We can't even reliably preserve large individual organs, let alone a human body. It's going to be, unless AI progress is like beyond my wildest imagination and it automates everything, it's going to take decades, at a minimum, if it's even possible to do that. So the alternative is information preservation is all you need. And the idea here is the information present? Because just because you're trying doesn't mean it's actually going to work. But you can ask the question, is the information present? And if so, then future medicine can work with that. And this is the idea behind Ettinger's idea, Evan Cooper, Ralph Merkle, Eric Drexler. This is really the idea. And people think that if technology improves in the future, that they will be able to revive people as long as the information is still present. So you can kind of think of people kind of in between here. We are, here, our organization is very much on the information preservation side, structural preservation, information preservation. And we're not embarrassed about it. This is what we think is the best approach. This is what we think should be done. We know we're not trying to say that we're going to do suspended animation. That's totally fine. Okay, so what is the advantage of using fixation and biostasis? Good point by Ashwin earlier that fixation is the gold standard method for whole brain structural preservation in neuroscience. So all of these connectomic studies that we have seen recently, this one from last year that was done in human brains, this one from earlier this year done in songbirds, they all use fixation because it's just the gold standard for preserving the structure. Okay, so then why have people not liked fixation historically? A few reasons. One is because it's not on the path to suspended animation. So if people think that we're going to get to suspended animation soon, then like Ettinger said, like you want to have your freezer program ready so that as soon as you start suspended animation, you already kind of have the infrastructure ready to start doing the storage. And a representative quote I found from Mike Darwin in a CryoNet post is saying the staff at 21st Century Medicine unanimously feel that they wish to devote their primary attention to research into cardiopulmonary cerebral resuscitation, organ preservation, and if possible, suspended animation. So this has been a big driving force behind researchers in the field for, since the 1970s. Another reason, some people have been concerned about the reversal of crosslinks, but I think most experts actually disagree with that. It's not just Eric Drexler and Ralph Merkle. Earlier this year, we did a survey of 22 biostasis practitioners, and the survey the preprint is available online. And we asked them whether they thought that preservation methods that use aldehydes would be compatible with revival via molecular nanotechnology if it is ever developed. And none of them said that they thought that would be unlikely or very unlikely for aldehyde-stabilized cryopreservation. The last reason why people have not liked fixation historically could be because, I think this is probably a significant reason as well, is that pure cryopreservation without aldehydes has a lot of other applications today that can make money. And money is very important in our society. So as a result of that, the pure cryopreservation methods have had and continue to have a lot more research funding. As an example, the Organ Preservation Alliance from 2014 to 2021 They helped raise more than $100 million in cryobiology funding from U.S. science agencies, donors, and industry. And in 2025, Until Labs reported raising more than $100 million in funding for research and development in reversible cryopreservation. Okay, so just a couple more kind of general slides about what we think, why we're using fixation. Sometimes people say, oh, it's not just the connectome, you need the biomolecules as well. To that I say, yes, you're completely right. We don't want to just preserve the connectome. We want to preserve the biomolecule annotated connectome. So we want to have the connectome, but also the important biomolecules in the original places. We want to do that across the entire brain. Unfortunately, it's not necessarily an easy problem. I would say we don't know how difficult a problem brain preservation is because we can't do revival yet. We can't do the information inference. So the conservative thing is to do a very good job of structural preservation and information preservation, do a better job than some people might think, and do the best we can. And then that way, if it does turn out to be a difficult problem, then we are more likely to have the information that we need preserved. So one example of why this information could be fragile is that there's long distance axons. So there's axons going all the way from the cortex to the thalamus and back. And if you don't have good enough preservation, you might not be able to trace exactly which axon is there. Also, at the synapse, I think someone was talking about this earlier. You were talking about this. At the synapse, it's not just like the presence or absence of a synapse, but could be synaptic properties based on the biomolecules at that synapse. And if you lose the precise organization of those molecules, then that could be really damaging. You might not be able to know exactly how the two neurons communicated with one another. So here we use aldehyde fixation for preservation. We believe this is the best method today for information preservation. We did a study we have from 2024. We used light microscopy on cortical tissue from a donated human brain. This was actually done at Mount Sinai where I was before I came here. So this hemisphere on the left was immersion fixed. The one on the right was preserved without cryoprotectant. It was actually preserved in a better way than just freezing the whole brain because it was sliced and then it was slammed between these metal plates, which is actually faster freezing rate than you would get. So this is probably less ice damage than you would get if you just froze the whole brain. But you can see when you rewarm the tissue and then fix it, you get these shrunken, distorted cells in large empty spaces indicative of ice crystals, which are concerning for information loss. So here are some structural preservation results from our methods, and you can read our paper for more information, but we have a human brain perfusion fixed after 4.5 hours of ischemia. The perfusion was not perfect, but one of the regions that got relatively good perfusion, we did electron microscopy on it, and we thought that it seems to have good structural preservation. Of course, it's not perfect. So, like these areas here are edematous. Okay. And also we were able to do tracing of these a dog brain that was perfusion fixed after 1.5 hours of ischemia, and we found that we didn't do this systematically, but the few cases we tested that you could trace the postsynaptic and presynaptic structures of a given synapse, which is basically the metric of synaptic connectivity preservation. So the last thing I want to discuss is our approach to revival. We have a section in our sign-up documents where people may record any revival preferences they want to be honored. If revival ever does become possible, we expect it will involve medical teams alongside a framework of rights for preserved individuals. Those rights would include independent oversight from judges, lawyers, ethicists, and others who will help to determine what procedures best serve the patient's interests. Part of our mission is to carry out the revival of our patients if and when revival technology becomes economically practical and humane. But we expect these revival procedures to be highly regulated. It's not like we're just going to go down to the vault and take the brains out and do some kind of revival procedure. There's no way that society would ever allow that, and nor do I think that they should allow that. Instead, it'll be highly regulated. So a benefit of this is that people's preferences in their sign-up documents and elsewhere will need to be respected about how that process goes. So conclusions, structural or information preservation is distinct from suspended animation. Suspended animation is a cause worth pursuing separately, and it already is. There's way more money in that than there is in structural preservation. The best known method for structural information preservation / information preservation in neuroscience uses aldehyde fixation. Aldehyde fixation is widely thought to be compatible with revival via nanotechnology by both the founders of nanotechnology and by experts in the field. And our mission is to provide high-quality structural preservation and allow individuals to express their own revival preferences. So I really appreciate all of our members and our funders, people who advance science by opting for brain preservation, and all the other team members here at Sparks Brain Preservation, and our collaborators. So thank you. Any questions or no? We all questioned out? Yeah.
Well, actually I have one. I'm one of these people that figures, well, continuity, personality is a nice to have. I work on stuff that's probably not going to get to see full implementation for centuries.
Mm-hmm.
And having examined a lot of things that were thought of 200 or 300 years ago and are getting implemented now, my usual question is, what the hell were they thinking?
Right.
And so, you know, for me, full revival with my lovely wife would be the gold standard, but the silver standard of explaining what the hell was he thinking might be really useful to some people in the future.
Mm-hmm.
And so there's the question of, are you bringing the personality back? Are you bringing the knowledge back?
Mm-hmm.
Are you bringing all the bad ideas back? And that's sort of some fine-grained thinking about this stuff that I don't think people are really thinking it through.
So your question is basically, what if it wasn't, someone's goal wasn't revival, but rather to like bring their memories to the future, so just help the future people in that way? Is that kind of what you're saying?
There was a Woody Allen movie where some blowhard was telling something to Woody Allen, and he pulled, in the scene in the movie, he pulls in this Nobel Prize winner and he starts explaining to this person why they were wrong.
Mm-hmm.
And he looks at the camera, don't you wish you could do this?
Mm-hmm.
So, that's influenced me a lot, thinking of, don't you wish you could do this with some past expert?
Right. Yeah, interesting question. We have had people, a friend of mine, John Smart, has talked about this too. Like, why don't you allow people to just donate their memories to the future or something like that?
Yeah.
And I think that would be maybe something you could write down in your revival preferences document.
Yeah.
Something like that.
If you can do the whole enchilada, that's fine. If all
Yeah.
you get is the memories, that's
Yeah.
something else.
Yeah, I think I think we don't know what's going to happen in the future. I don't think that's what most people want. So I don't think that makes sense to like offer as like a major thing that like is going to get people super excited about it. But there's a subset of people I've heard of who mention that, and I think the way to do it would just be to write that down in your revival preferences.
But then the question would be which memories.
The whole personality, throw them away.
Right. What is that?
Then the question would be which memories do you want to share with the future, and how would they ensure that only those are preserved?
Well, maybe all of them. I don't know. I think it's probably challenging to figure out like which memories are which. It's probably a challenging thing.
If all your memories are preserved, then you're not preserved. You wouldn't be conscious, but all your memories would be shared with people.
Yeah, I mean, it's so hard to think what's going to happen in the future. Some people think that like people's brains are going to like merge in the future, but I think it's just. I think for most people who are thinking about signing up for this is not the kind of thing they're thinking about. They just kind of want to come back to life. I mean, like, I know when I was thinking about like signing up for that, it was like not about like memory preservation. Like I'm just trying to like not die, So it's really not complicated. Who knows what's going to happen in the future? If like society all wants to like merge into some big mind and like that makes sense for some reason, then I don't know. Hopefully I'll be around to like help cast my vote.
What can you tell us about Hiber?
Oh, I don't know much about them. Yeah, Alexander German is seems to be kind of a phenom. He's done a lot of really good research really quickly. They are interesting because they're kind of another one to straddle. He reminds me of Ettinger and of Evan Cooper because he's kind of straddling the suspended animation and information preservation sides. So right now what Hiber is offering with their Atlas program is a fixation for structural preservation, but most of their research is on suspended animation. So it's kind of interesting to have one organization doing both. I would say, my personal opinion, is actually we do need some research on this side. Like some people need to actually do research on like figuring this thing out, and like it's gonna like take some money and some effort, and like I know suspended animation is like super exciting, but like let's like do this like well before. Okay, then when I say this, people get mad at me and they say, "Oh, you don't want suspended animation? Like you're a horrible person." No, actually, I do want suspended animation. If they figure it out, like that sounds great, but like we shouldn't. I think, as one of my friends pointed out, we shouldn't put all of our eggs in the suspended animation bucket. Like we need to like also just get really good at this, because for many of us, this might be the only thing that's available when we legally die.
To any on that point, I think now it has changed because of our Deming sort of company. But actually, although maybe scientists and the general public demand to want to see suspended animation, a lot of the research, even sort of in traditional cryo, was never aimed at that, right? So like even 21st century medicine had a whole body program, but it was more aimed at looking at eye formation and structural preservation than actually revival. So actually that research actually has not been sort of really pursued sort of until recently. And of course I'm doing it, but that's more because I want to characterize sort of how hard it is actually to do it.
Yeah.
And because I think we all have a good feeling how hard true reversible whole body cryopreservation is. But defining that sort of, I think it's really important, and it also can provide some realism sort of this debate. Like for example, one thing people often seem to think is like, oh, it should be very easy to take a small mammal at least.
Right.
The problems are almost as huge, and in some ways, like microsurgery, they're actually even harder, you know. So it's like, I get it all the time. Oh, why don't you just revive?
Yeah, for sure. Yeah, I think I agree. I think a really good paper, or a couple papers showing how difficult a problem it is, and bounding how difficult a problem it is, would be beneficial just for advancing the debate.
Yeah, like for example, like one thing I never thought of before I started doing this project is like we say, like introduce protect and we remove it. What does removal mean? Because if a very small fraction is left behind and you go to lower thermal temperatures and it's ethylene glycol, it will just convert itself into toxic compounds and they're dead. Right? So in traditional cryo, you never sort of think about some of these issues, but for whole body, that sort of would matter a lot. But as I said, I think until Laura Deming, there actually has never been in cryonics a focused suspended animation. What you could say is like almost all the research was aimed at viability, right? That's certainly the case.
For back to the question about the, I'm glad when you mentioned Benjamin Franklin and his Madeira fly experiment. I love that whole thing. I have that photo of my house.
Oh, amazing.
Madeira at my wedding.
That's amazing.
But I'm half joking with this, but not really, just as a side thing. I want to reproduce the drowned flies in Madeira wine experiment, and I'm asking around anybody who wants to do it with me.
Yeah.
Because just for fun, but it's kind of interesting. I want to see if what he was seeing was actually what was happening there with the Madeira. I thought some other ways in which it might not have been what he thought it was, in terms of the fly actually being dead and what have you. Many cases.
Well, the fly was probably not dead, right? It was just drowned.
So you can surprisingly take flies and just toss them in the freezer overnight.
So is this already been reproduced?
I did that when I was 10.
I didn't realize.
But as many as
Okay, what specific?
in the freezer.
So that's a good lead. What specifically?
We should revisit Madeira actually. It is the best crack detected known to man.
Yeah.
Which, by the way, there's a fourth column there, and after that, there's where you also have free ice cream ponies.
He said there's a fourth column where you have free ice cream and ponies.
But it would be a good experiment because the beer would be at room temperature, and that would be kind of something.
No, I like it. Yeah.
Proof of concept for the chemopreservation versus cryo.
Yeah. I asked Claude. I said, Claude, is this actually true? And Claude said it was. Still must be true. Everyone knows I rely too much on AI. I do think about my own brain too, I promise.
But just wondering on the process, how does the aldehyde get through the cell membrane? Is it through little tears?
No, great question. It's lipophilic. So we don't have the issue with blood-brain barrier, cell membrane, just goes right through. It actually causes some interesting phenomenon because it's lipophilic, it doesn't exert an osmotic force when you perfuse it. So the effective osmotic concentration is lower than the concentration you measure on an osmometer. So basically, when you think about the osmotic concentration of what you're perfusing, you need to think about the base, the carrier solution, basically, for the fixative.
Aldehyde actually has multiple forms in solution. One of them's a ring and one is a linear one. And it's only the ring one that goes through membranes like they don't exist, but also it rapidly interconverts between the two, so it's faster than water, and so it doesn't count osmotically.
Mm-hmm. Yeah.
So Andy, the concentrations of formaldehyde you prefer for immersion are pretty high.
Mm-hmm.
If you would perfuse with them, would they be too
Would they what?
Too like, too osmotic, like.
No, it doesn't have an osmotic force. So that you have to worry about the osmotic concentration.
Not short term. Like even if you use very high concentrations of formaldehyde.
What?
It doesn't
No.
force until you're
Yeah.
even at 7%, which is like 2,000 milliosmoles or something. And it still is pretty negligible.
If you say
7% weight of light, which is like
Yeah.
well, it's usually talking about 20% for immersion.
Yeah, we're doing 20%. That's what they recommend in the neuropathology literature. Like that's what they will do. It just if you have more of it, it just penetrates faster.
Does it shrink the outer layers when you do that, or
We haven't noticed that. To be fair, we just recently started switching to 20%, but it's like very widely used in neuropathology.
I would be inclined to say even if you have something that penetrates really fast, if you have a very high osmolarity gradient, you might still get some, at least 10%.
Yeah. It's an interesting question, but we're adding to the osmotic concentration by also adding mannitol. But I think that would just improve the perfusion.
That was going to be my next question. With the discussion on shrinking, you said you were adding that to improve dehydration a little bit. Is there some optimal amount of shrinking that you're aiming for, or dehydration you're aiming for?
Well, it's a great question. We don't really want dehydration, but dehydration seems like it's a way of improving perfusion, because one of the barriers to perfusion is basically there's edema of the cells right around the blood vessels. And so if you can reverse that, then you can probably open up some other capillaries and it improves the perfusion. But it's a trade-off, and exactly where that should be is a tricky research question whenever you have a trade-off like that. Probably there's a bunch of different things that would all work decently well, but yeah.
it's important to know you can decouple dehydration and structural deformation, right? Because if you soak a cell slowly and increase concentrations of cryotechnology, you can dehydrate it almost 100%, right? But it still is exactly the same geometry.
Yeah, good point. All right, thanks so much, everyone. I really appreciate it. So maybe we should just chat for a while here before we call it a day.